All right, welcome everyone to our AI seminar. It's my great pleasure today to introduce Julien Emile-Geay, who is a professor in the Earth Science Department at USC. And sorry about this. Julien is a climate dynamicist and paleoclimate data scientist, and he holds a BS and an MS from the École Normale Supérieure in Paris, France, and he got his PhD from Columbia University. His research focuses on using deterministic and probabilistic models to create mathematical representation of the climate system to shed light on its long-term behavior. On a more personal note, Julien was on my advising committee when I was a PhD student. We've had pretty much 15 years now of collaboration. But his first introduction to ISI was school Yolanda to work on standardization of paleoclimate data. Julien?
Hello, everyone, and thank you for the introduction. So let me share my screen. All right, and I will be talking about data standardization today, in part. So I have not timed this talk, so I hope I'm going to be we're going to be doing okay on time. This is probably not the usual type of seminar you get in this series. In fact, I have attended some of them, so I know that's the case. And as Deborah said, my background is not in computer science or machine learning, although these are, I'm a user of some of these tools, but definitely not a producer. So what I want to do today is sort of take you through some of what I think are the biggest unsolved problems in the field and where I think various artificial intelligence tools can help. It by no means will be an exhaustive list, but I chose to speak of what I know about. So that restricts the range, of course, but hopefully that will give you a good overview of some interesting climate problems, paleoclimate problems, where AI can play a role. So without further ado, the first questions to tackle is why study past climates in the first place? Because you might say, well, we have maybe 100 years of instrumental observations, maybe that's enough, that we have satellite observations that produce terabytes of information every day. So why do we need to go and bother about past climates? And there's basically three reasons for that. This is a picture from the last IPCC report. Hopefully all of you have heard about the IPCC, the Intergovernmental Panel on Climate Change. And that serves basically as the most authoritative review of the state of the science over time. I see activity in the chat already. Okay. Yes, please ask questions at any point. And one way in which you can use the paleo record is to basically give context to recent trends. So if all you see is, this the warming over the past 150 years or so, you may wonder how anomalous it is in a long-term context. And indeed, we see that with our best estimates of the climate of the past 2,000 years, it is highly anomalous, both in terms of the amount of warming, but also in the rate of warming, which is truly unprecedented. So that's one first use of paleoceanography, paleoclimatology. The second one is to hunt for analogs. So what you see here are various projections using climate models, so physics-based computer programs that try to emulate the behavior of the Earth system in different climate scenarios, as they are called. So basically scenarios on human development and various choices that we would make. And one of the things that people ask is, say, well, how, have we seen climates like this before? Have we seen climates where it's, 4 or 5 degrees warmer than it is now? And the answer is yes, we have, but we have to go back quite a bit, at least 5, maybe sometimes 20 or even 50 million years. And these analogs are extremely helpful because they can tell us about things that we wouldn't know otherwise. For instance, they can tell us, in which climates have we had ice sheets covering parts of the northern hemisphere, like for example, the Greenland ice sheet, or on what type of situation is Antarctica covered in ice. And we would not know that. Models are not good enough to really tell us these things and inform us about these thresholds, but the paleoclimate record can do that. So that's an important role as well. And then finally, there's another role which is becoming more and more important now, is to constrain the processes themselves. So actually using the paleoclimate record to try and constrain some of the fundamental physical processes that will play a role in the future. And I'll show an example of that. In particular, one thing I'll be talking about today is something called equilibrium climate sensitivity. Climate sensitivity is a bit of a magic number. It's not a very useful metric observationally, because it turns out we will never actually observe climate in equilibrium. Climate is always affected by one thing or another, so it's never truly in equilibrium. But it turns out that with climate models, you have the luxury of basically running them to equilibrium. So you can say, what would happen if I doubled the amount of CO2 in the atmosphere from what's called pre-industrial concentration? So basically what things were like in 1850 with 280 parts per million of CO2. And if I double that to 560, that's something that was first done in a 1979 report by the National Academy of Sciences that was actually headlined by my academic grandfather, Jules Charney. And in it, he said, well, this is a useful metric of how sensitive a climate model is to CO2, carbon dioxide being the main byproduct of our civilization. And as you can see, this is a bunch of different climate models. Don't pay attention to too many of these acronyms, but these are climate models generated by various groups around the world, mostly in the US, Europe, and Asia. And you can see that all of these models have quite different values for this metric. With the most sensitive models warming up by over 5 degrees when you double the amount of CO2 in the atmosphere, and the least sensitive models, I'm not sure if it's a coincidence, but they're both Russian models, not showing much warming at all with CO2. And then you might say, okay, why do I care about that? This is a fairly abstract metric. Well, it turns out that that metric correlates with a lot of things that we care about. For example, damage from extreme weather, the ability of plants to tolerate various climate ranges, and impacts on agriculture, impacts on human health, and so on. So while it's not a perfect metric, and in itself it's fairly abstract, it's been sort of a magic number because it's one metric that summarizes a bunch of things and correlates to some extent to things we care about. And the history of this has been very frustrating because, as I said, in 1979, Charney, with only 2 climate models, basically said, he had one model with a high sensitivity, one model with a low sensitivity, and he basically made an educated guess. He said, look, climate sensitivity seems to be around 3 degrees plus or minus 1.5. So it's anywhere from 1.5 to 4.5. And over time, that range has remained stubbornly constant. In fact, we thought we were making a bit of progress in the early 2000s. These are what's at the bottom here are various reports from the IPCC. And in the 2013 IPCC report, they actually greatly increased the range of equilibrium climate sensitivity, meaning that they recognized that we actually had a lot more uncertainty about this. And so in AR6, one thing that happened is that there were several models, including the flagship model by the National Center for Atmospheric Research. So it's called CESM2. That model shows very high climate sensitivity, around 5.5. And an embarrassing thing is that nobody could quite understand why. It turns out people started tracing that to various parts of the physics, how the physics is encoded in the model. And so you don't need to pay close attention to that. But basically, it has to do a lot with clouds. So the way clouds are represented in the models really governs how sensitive they are to climate. And you can see how these various modifications that were made from one model version to another went from something right in the middle of the ballpark of ECS, around 3 to 5.5. And this is another way of looking at that. Basically, for these different models, climate sensitivity correlates very highly to a cloud feedback parameter. And I'm not going to explain what that is, but it's something having to do with clouds. Now, clouds are one thing that models do very poorly, because if you look out of your window right now, if you're lucky enough to have a window in your office, I know several people at ISI are, it's possible you can see some clouds in the sky right now, and you can see that they have relatively small scales. When we try to represent those in a climate model, it becomes very difficult, because this is an example of what we call a subgrid scale process. It's something that's within the typical grid scale of what's represented. So we basically have to make an educated guess as to what the cloud is doing. And so there's various ways of going about that, some of which actually involving machine learning. Some people are basically trying to use machine learning trained on satellite data to fill in the gaps. Some people are trying to use do this from first principles, using field observations. But the basic idea is that the uncertainties we have about clouds, which I show right here, translate, they overwhelm all the other sources of uncertainty that we have. So it's not that we know everything else about the climate system, is that the uncertainties we have about clouds are so much bigger than anything else that overall they're what governs the main uncertainties we have. Now, the way this feeds back into paleo is that it turns out, with modern observations, we can't do a whole lot about that. A lot of this uncertainty that persists to this day, that has persisted for over 40 years, has not been resolved by modern observations. But paleo observations, which are basically an out-of-sample test of climate models, should be able to constrain this. And so there's several ways of going about this. One way I'm going to talk about today, because it's most closely associated with my research, is this topic of emergent constraints. Emergent constraints is basically a way that you have two variables, y and x, and you cannot directly observe y, but you can, for example, simulate it in a climate model, but you may actually have some observable x that you can constrain from observations. And so basically you use the observational constraints on x to give you some kind of constraint on y. And so in this case, for example, Earth system sensitivity, very closely related to equilibrium climate sensitivity we were discussing. Well, if you see a relationship, an emergent relationship in the models, you can use that to basically constrain with observations. Now, of course, it's very tempting when you see a scatter plot to go on a fishing expedition and try to fit any kind of relationship to it, whether linear or nonlinear. So climate scientists like to have a few more qualifiers to that. There needs to be a physical relationship for why there would be a relationship between y and x. Ideally, this needs to be present in at least 10 different models, so it's not a fluke of the implementation of one particular piece of computer code. And out-of-sample testing is encouraged. So one particular example I'm going to show you has to do with the last millennium. So in 2018, there was this paper that developed the so-called Cox metric. I'm not going to get into the details, but it has to do with basically how fast the climate system gets back to equilibrium. And they were able to show that there was fairly noisy but existing relationship to equilibrium climate sensitivity. And in that model, they only used the very short instrumental record, actually, I think since 1950 or so. And so one natural thing is to say, well, what if we used a longer time span? For example, what if we used the information we have about climate over the past 2 millennia to constrain that? And that's exactly what was done in this work by colleagues of mine at UCLA on a grant that we have together. They took reconstructions that I helped produce. So these estimates of temperature of the past 2 millennia, which I'll explain in a minute how we even get to that. But they basically use this to constrain climate sensitivity in the model. And basically, I'm going to skip over the details, but there's a few wrinkles to that. But what you get out of this is some kind of, you get some constraints depending on how you implement this that help refine the range of equilibrium climate sensitivity. In particular, we can basically rule out things that are below 2.5 and above 4. So it's a lot better than what it was like. And in particular, we can say that the model I was talking about that had a climate sensitivity above 5 definitely is too high. So that's one constraint, actually from a fairly noisy data set. And it turns out, this is done in a Bayesian framework. So you could potentially be combining this with other sources of observations and get smaller and smaller error bars as a result. So that's basically one motivation for what I do, is that by using the paleoclimate record, you can obtain quantitative constraints on a key metric of climate that informs a lot of other things, including mitigation scenarios, public policy, and a whole bunch of things, economic planning, all of that. Does that make sense so far? Stop me if it doesn't. So where I want to go with this now is sort of rewind the clock to this. How did we get curves like these? How did we reconstruct climate over the past 2 millennia? And how in general do we estimate and reconstruct climate? So again, this is coming back to that picture from the IPCC, which is based on this work that I was involved in, that was published in Nature Geoscience. And in fact, I was involved in 2 different methods, 2 different curves on this ensemble. So basically what this shows is 7 different attempts at statistically inferring climate variations from the paleoclimate record. And I'll get into how that's done in a minute. So what are the data that went into this? Well, before the era of instrumental measurements, where we actually had thermometers, barometers, and so on, it turns out that the only way we can really tell what was going on is by using natural archives. For instance, tree rings, ice cores, sediment cores, corals, or in some cases, cave records. And so let me give you an example. Why do we want these things? Because they're sensitive to the environment and they record some things, whether it's, for example, the width of a tree or the chemical composition of a layer of ice or a layer of sediment, tell you something about the conditions in which these records were accumulated. The second reason why we like particularly these archives is that they can be dated very precisely. So for instance, the ice you could see on the previous slide was very banded, and so you can count the layers and they tend to have an annual banding. There's some, some double counting that can happen or some undercounting, but basically if you have enough replication, you can beat those uncertainties down. And you can do the same with trees. You can core a bunch of nearby trees and look at the pattern of growth. It turns out that each tree has a unique history, so you can read those things like a barcode. And if you see, fairly consistent barcodes from one tree stand to another, then that's a pretty good indication that they were recording the same environmental conditions. And again, you can count these rings. You can see very similar patterns from tree to tree, and so you can replicate this. And tree ring chronologists are in general very confident about their reconstructions down to an annual scale. And we could do the same in corals, we could do the same in lakes. So we're pretty confident about when things happen. Now, the next part of that question is what happened? So trees, tree rings record basically the conditions of growth. some of which may have to do with temperature. So for those of you who've traveled to the White Mountains in California, about 4 or 5 hours north of LA, you may have seen some of these stubby trees. They're called bristlecone pines. These are some of the oldest beings on Earth. They live longer than sequoia trees, actually, even though they're much smaller. They basically live very slowly. They accumulate resources very, very slowly, and they live a long time, like 5 or perhaps even 6,000 years. We don't know exactly how long the oldest one is, but it's not uncommon to find chunks of wood like this that represent several thousand years worth of growth. And if you look, this is a ponderosa pine that doesn't, lays down much fat to rings. And basically by looking at the pattern of growth, you can get an idea of what environment that tree was subjected to. Now, of course, growth for a tree depends on various things, some of which are temperature. So for example, for these trees, there's fairly abundant snowpack, so they're not too bothered by the lack of water, but they really care. These are pretty lonely, windy, and cold places that they live on, and so they tend to be very happy when the temperature warms up and not grow very much when the temperature cools off. So they're pretty sensitive indicators of growth conditions. And we can use different trees for different purposes, whether to reconstruct drought conditions or reconstruct temperature conditions, but that's the general idea. I hear somebody else being unmuted, so any questions? Maybe not. All right, so I was part of this compilation effort, which was a large international collaboration. It involved 98 people, I think, covering 4 continents. And what we did was to basically crowdsource the curation of a fairly large database. It won't look large to you, most likely if you used to work with big data, but it's large for us. It was something like 700 records from 648 locations. They span a fairly big range in resolutions, meaning we had some corals with 1 data point every month, or even every 2 weeks, down to some lakes where there was basically 1 data point every 50 to 100 years. The vast majority of the records in this compilation were trees, which you see here in green, and they had an annual resolution. And basically, this was like the biggest effort at the time. This was published in 2017. This was the biggest effort to date in synthesizing information from this broad set of sources. And I like to call this, it's not big data because all of this basically fits on a thumb drive. It's a couple of megabytes at most. So for those of you who are dealing with, gigantic data sets of several gigabytes or terabytes, or probably even bigger for some of you, this hardly qualifies as big data. But instead, I prefer the term broad data because they cover, they come from all kinds of different places. They're very diverse in their aspect and how they come to us. They're basically all time series data, so they have that in common. But the interpretation varies a lot. And for instance, it's important to document that. They're very heterogeneous, basically. And so I like that term broad data. The one thing they have in common is all of these were quality controlled and they were deemed to be temperature sensitive. So as I said, some trees are limited by moisture conditions, some trees limited by temperature. And in this compilation, we only included the trees that were believed to be temperature limited. And similarly for all of the other series that were included, they were meant to be reflective of temperature conditions. So, okay, that's the data. Now, how do we weave those data sets together to arrive at a reconstruction of temperature? Because with very few exceptions, none of these things actually record temperature itself. They record something related to temperature, what we call a proxy, right? So you're probably familiar with the term proxy, mostly in the legal sense. A climate proxy is something that tells you about what you want to know, but it's not exactly what you want to know. So none of these things tell you temperature in degrees Celsius. They may tell you ring width in millimeters, or they may tell you, the ratio of some chemical elements in millimole per mole, but they're not temperature. So how do we translate that? So in that paper in Nature Geoscience, I was involved directly in 2 different statistical methods that did that, and I want to spend a minute describing that. So this is the so-called data assimilation framework that we use. This is using an ensemble Kalman filter. And this is basically fusing these observations. In this case, we only use trees, corals, and ice cores. And we're fusing that with information from climate models. And basically, the models give us a sense of how things vary over space and also how variables are coupled together, like, for example, temperature and moisture. The observations give us the timing of fluctuations. And then there's a bridge, which we call proxy system models, which in this case are very simple. They're basically just linear regressions that give us that scaling between, let's say, the width of a tree ring and how many degrees Celsius happened on the ground. And so basically you can take this algorithm, you put in the information we have from the Pages 2K network that I just described, the paleoclimate data sets. You use some instrumental data for calibration, and you get an estimate of temperature, for instance, over the 20th century, that is actually very, very competitive with other instrumental products. And to be fair here, for example, we only trained the model, we only trained this method on year-to-year variation. So for example, we removed the long-term trend, and we only trained the model with year-to-year variations. And it turns out, even with that, the model was able to recover the long-term trend extremely well. So we're pretty happy about that. And spatially as well, we can test that we're doing this at most locations on the globe with high scale. So this is a metric that's basically related to the mean squared error. So one form of loss function, if you will. But basically everywhere that's red is good, blue is bad. You can see that most places on this map are reconstructed with some skill. And so one of the nice things about this method is that it actually gives you a whole ensemble of trajectories, and it gives you uncertainty quantification over time. So one key aspect is that the uncertainties grow back in time. And that's because you have fewer and fewer observations of high quality as you go back in time. So that's one thing to be aware of in what we've done so far. And we're still working with those uncertainties. Here's another fun visualization of that, if you like joy division. But anyway, the point is that you get a statistical distribution at every point in time that you can then leverage for all kinds of inference. The other method was a more straight up Bayesian hierarchical model, which I'm not going to get too much into, but just know that it basically leveraged information about what we think is causing variations. So variations in the output of the sun, variations in the amount of CO2 in the air, variations in what volcanoes are putting in the atmosphere. And based on this, we got different reconstructions of temperature. And we were able to do some fun things like, excluding the idea that the sun has really any measurable impact on climate over the past 2,000 years. All right, so that's basically how we got to these curves that I was telling you about. But again, I told you a very sanitized and simplified version of that story, because where I started with this was the Pages 2K dataset. What I didn't tell you about is what it takes to actually generate a data set like that. And that's what I want to talk about now. So how do we mine the paleoclimate record? Well, first of all, I want you to be aware of what it takes to do paleoclimatology. There's actually multiple steps involved, each of which involving people with very different types of expertise. This is actually a slide I recycled from one made by Deborah a while back. So imagine, for example, if you're talking about ocean sediments, which is what her expertise is about. Well, first of all, you have to go get them. So you have to get some big ships out in the middle of the ocean collecting cores. So you basically lower a metal tube that's about 35 meters long into the mud at the bottom of the sea. It can be surprisingly easy to get that tube bent to the point where you can't recover the data. So it's already quite an exploit when you manage to bring the mud back onto the ship. So that's the first step. And to be able to even decide where you go and get these data, you need to appeal to various fields of knowledge like sedimentology, seismology, ocean engineering, to basically even just retrieve the mud. Then you have a bunch of people like Deborah who have expertise about the mud and who know how to make it sing, so to speak. So they know how to, what organisms to look for in that mud, basically the shells of unicellular organisms that lived a long time ago and that recorded climate conditions at the time that they were alive. People with that expertise know how to basically analyze the chemical composition of these shells using what's called mass spectrometer, and eventually get to time series that you can then access by various ways. And yes, for a long time, people would basically just email each other spreadsheets, which sounds incredibly barbaric, and it is. I'm not going to make excuses for my field. And unfortunately, people are still doing that today, even though there are websites like, for example, the one hosted by NOAA that host a lot of these data sets. And when we started this work, it was a big question for us about how we curate the best versions of these data sets, how we make the selection of these data a transparent process, and how we perform queries, for instance, to go seek out only the data that we think is relevant to a particular question. And because the data were not standardized, because basically they were living in people's drawers in some cases, or in people's spreadsheets, and they all use different conventions for how they would describe that data, it turned out to be surprisingly labor intensive to even generate a database that you could then use. So, once you have things that are standardized, you can write, using any programming languages of your choice, you can write all kinds of statistics and signal processing codes that will perform miracles for you. But, we found that the limiting step was really curating the data. So it turns out, there are some steps about which we can't do very much, right? There's only so much funding to go out and collect new data. Everybody's aware of that. But where we found was our biggest opportunity for impact was in helping streamline the process of curating these data sets. So now that we've done some of this, we've been able to actually write some really awesome packages, and Deborah is involved in this. We've written a lot in Python, which I know some of you work with. Here's actually a link to a software catalog that I think was built with tools made at ISI that show a lot of different codes that Deborah, myself, and collaborators have developed over the years. And yes, Yolanda, I think this is a software catalog that you had some input in. So anyway, nowadays we have enough standardization that we can build open source object-oriented codes, but the hard part for us was to get to standards. Without standards, all of this falls apart. And when we began this work, so Yolanda and I, as well as another colleague at Northern Arizona University, got a grant funded in 2016 that was called Linked Earth. And so if you see any Linked Earth business around here on my slides, that's what it means. And we were funded by the EarthCube program of the National Science Foundation, ostensibly to help standardize paleoclimate data using some semantic web technologies, as well as some good fashion, community engineering. I have to say, when we started that work, I was a little bit naive about what we meant by standards. And what we found along the way is that there's basically three things. And I like to compare this to the system of index cards that you have in a library, a good old-fashioned library. So if you think about how, if you want to ever find a book in the library, you need to have an index card for the book. and you need to have a place where you house that information. That would be the, the container, in this case, this piece of furniture where you know where to look for index cards. So we didn't have a container like that for paleoclimate data. And so we had to invent one, and I'll talk about it in a minute. We call it the linked paleo data format, or LIPID for short. The other thing that you need for a classification system like this to work is you need standard terminology. You need a way for the index cards to use common terms and have a uniform meaning assigned to these terms. So basically you need an ontology, and it won't surprise you if you know anything about Yolanda that we ended up using an ontology for this. And then finally, and this is the part that we didn't quite appreciate at first, is that this whole system, no matter how well designed, can completely fall apart if people don't actually use, if they don't input the information properly, or if they mean different things when they write a certain abbreviation. And so we realized that we needed community standards. We needed guidelines of what it takes, what kind of metadata needs to be entered for somebody to be able to reuse a data set. Otherwise, the whole system falls apart, and you might as well, my analogy to this was like, you need people to put back the index cards where they belong after they've done them. If not, you might as well just have them in a random pile in the middle of the room. So let's look at these three things in turn. The first one, linked paleo data, is this container that we devised that was basically the data in a simple CSV format with a bunch of metadata that in JSON, observing some existing standards, like for example, BibJSON for bibliography information, GeoJSON for geolocation information, and things like that. And with containers like that, we were able to write codes that could access the data the way we wanted. But we still had to define basically the labels on these boxes in a uniform way. And that's been surprisingly difficult to do. So we ended up creating an ontology, the linked earth ontology, that Deborah and Yolanda were very involved in, along with other people working at ISI, like Daniel Garijo, who was there a few years ago, and Varun Ratnakar. And so now we have an ontology. And one of the things we can do with the ontology, which is current work that Deborah can tell you about, is that you can build actually a graphical database, basically a knowledge graph, that can enable very complex queries in a very short amount of time, which is not something that current classification systems were able to do. So that's one very clear advantage of having an ontology. It took us a little while to get there, but the investment is paying off. And the third part of this standardizing, this reporting standard, as we call it, is something that was the result of a crowdsourcing process. So we had 135 researchers that voted on more than 600 properties, eventually creating a system like that of many trees pertaining to different types of paleoclimate data. And that's basically what it took to get to that space where we could get Pages 2K data. So a little bit more about the community aspects of this. The Pages 2K network actually had different regional groups that contributed to it, from North America, Asia, Africa, Australia. There were a group in Europe, and there's a group that was focused on global oceans. And basically the way that people dealt with this is like we had some Google Sheets where people would input the primary information and the metadata. Then our friend Nick basically waved the magic wand programmatically to turn that into this linked paleo data format that we talked about. And once you had that, then you could start writing codes that could make use of this to produce the reconstructions that you saw, and then connect to other parts of the social technical ecosystem. So that's basically, sort of, to make a long story short and to summarize the work of literally hundreds of people over many years, that's what it takes to go from paleoclimate observations all the way to constraints. So it took a lot of standardization. It took definitely the development of various methods, statistical methods, to get to a point where we can actually use these very unique types of data sets to produce quantitative constraints on a metric as essential as climate sensitivity. So I've summarized a lot of different steps here in just a few minutes. And in the rest of the talk, I basically want to tell you about where I think AI can play a role in basically, for example, that particular pipeline. The fundamental challenge is basically to take information from the proxy observations themselves, the raw data that we get from the Earth, and incorporate that into our knowledge about climate. That's the grand challenge. And until recently, it was not possible at all, or it's very difficult. So you've seen already with the work that we did with Linked Earth, with some people at ISI, including Deborah and Yolanda, you've seen some examples of how some AI tools can help with data standardization. But I want to offer a broader perspective so that perhaps some of you will have ideas on how to collaborate to do these things better. So my first conclusion is that past climates are relevant to our future, and that's because the further back you look, the further you're likely to see. Paleoclimate data are not big data. They are what I call broad data. They're very diverse. They come from different places, different archives. We measure different things on them. They're generated by different people with different cultural backgrounds and different expertise. And so there are a lot of human elements in actually building a data set like that. But at the end of the day, we can get quantitative constraints on key climate variables. And also, I did not talk about this today, but we can actually constrain key climate processes using these data, which is very new and very exciting. But I want you to remember these constraints are very hard to get. People have to sweat an enormous amount to get a single data point for these things. This is not like social media data or something that gets generated in terabytes every day. It takes years to even have a few dozen data points at a single point on Earth for some of these archives. And so part of our challenge working in this field is how we make the most out of these data. All right, so I want to close here about a discussion of where I see artificial intelligence helping with various aspects of this information pipeline from past climates to modern climate and future climates. First of all, I've shown examples here about how we can reason over the data themselves. Deborah, for example, was involved in this recommender system that I think she's presented before, at least to some of you, to better annotate these data. I was also mentioning this knowledge graph that can enable better querying. I have one graduate student at the moment who's generating a package, wrote a package called Ammonites that's going to eventually carry out some automated detection methods to classify various types of events in the paleoclimate record. For instance, one thing that paleoclimatologists are very interested in is abrupt events. Events that happen seemingly out of nowhere, that seems to be fairly high impact, high amplitude, and that could potentially happen in our future. So if that's the case, we want to know what are the warning signs, what are the precursors for these types of events, and there are machine learning methods that can help with that. Perhaps there's also tools that would help with curation, and I have ideas about that, but happy to discuss it with anyone who's interested. Obviously, there's a lot of work at ISI on dealing with workflows, and there are a lot of workflows in this field because of the diversity and the breadth of the data that I could see AI helping with. For example, there's different people coding in different languages that sometimes need to merge their work, and there's a space for workflow management systems like Wings to be able to do that intelligently. Overall, even though we've made a lot of progress, I think there are still issues of reproducibility and replicability in the field. And again, I think workflow systems could help with that. Another big impact where AI is being really is exploding right now is in building alternatives to physics-based climate models. These models are very expensive, and as we've seen, despite the enormous expense of human capital to write them, and also computer and energy capital, honestly, to run them, they can still be very uncertain. And so there's a large space here for emulators that can be needed for climate prediction, but also for the types of data assimilation that we do here in paleoclimate. So if you have interest in that, I'd be very happy to talk emulators. And lastly, there are groups already, actually there's many groups that are doing this because it's very trendy, who are doing their best to learn from theory and observations and incorporate that in climate models. One example, for example, is the Clima Alliance at Caltech, but there's multiple examples of that in the US and other places at the moment. Finally, I think what I've shown you here is using fairly linear methods, but proxies can often have a nonlinear relationship to climate, and there's definitely some machine learning methods that may help, with the exception, of course, of naive deep learning. We don't have enough data to really do any deep learning, and the field is a graveyard for naive approaches. So anybody who's tried to apply off-the-shelf methods to paleoclimate data usually breaks their teeth on them because they violate all the conditions that people usually write their methods around. So while I think there is definitely a use for machine learning and AI in general, it definitely has to be heavily tailored to these applications. That's where I'll end, and I'm very happy to entertain questions. And there's still a bit of room in my schedule if you want to meet this afternoon after 3.
Thanks, Julien. Any questions? So if you're a panelist, you can unmute yourself. Attendees, chat.
I have a kind of specific question. I was going to ask you this during our meeting later today, but I know you talked a little bit about Bayesian methods that you use in your work to actually quantify some of these. Could you give maybe a few more sentences of description of the types of methods you use, and maybe kind of what their limitations are, strengths, kind of whether there's room there? Some interesting follow-up.
Yeah, absolutely. So, the Bayesian hierarchical models have been devised to link these observations to the underlying process, for example, temperature. So that would be at the process level of a Bayesian hierarchical model. And, because of the difficulty in setting up these models and doing inference on them, they've remained relatively primitive in their formulation. The more complex and realistic the model, the harder it is to fit, as you know. And there's also not always enough modern observations. That is sometimes a limitation that we have. So we don't have enough modern samples to actually properly calibrate the model and estimate parameters. One advantage of the Bayesian framework is, of course, with Bayes, you can do inference with just one data point, right? As long as your prior is strong enough. So if you're confident enough in your prior, if you can encode some scientific information via a prior, which is very useful. So we've definitely done some of that. Where I think the field kind of got stuck is, finding good distributions to represent spatiotemporal processes. I don't know if that's your area, but there tends to be this assumption of isotropy. So for example, things only depend on distance, they don't depend on direction, which is not a very useful assumption. And we found that the climate system is highly anisotropic. There are things like mountain ranges, whether you live east or west of the Andes, you have a different climate, for instance. There's differences between oceans and land. And so there's all kinds of reasons why these assumptions break. So in the original versions in which these models have been applied using pretty simple distributions for the priors. They weren't terribly useful, but there's definitely a lot of room. So I've played with, for example, Gaussian graphical models that are much more flexible in that respect. And you may have ideas about other types of inference or other types of models that could work better. Does that answer your question?
Yeah, that answers my question. I don't necessarily have a lot of depth in this area, but I think your answer is really interesting. And I think there are lots of places where that occurs, right? If you think about like crime in neighborhoods, two adjacent neighborhoods don't necessarily have the same crime profile. So it's not a linear kind of distance-based model. So I think that's something we see across many data sets. And it's interesting that, it's also a deep part of the research you're doing.
Yeah,
happy to discuss that later. Yeah.
Absolutely. Great. I look forward to that. I see Yolanda has her hand up.
Hi, Julien. I really enjoyed the talk. It is nice to see the whole, the broader perspective and to hear so much about the climate research questions and directions that you see. I wanted to ask you a broad question about AI and climate. So I know that there's a lot of machine learning researchers that have made good collaborations with climate researchers. People like Vipin Kumar and Claire Monteleone. Vipin ran a big expeditions project that it has a great reputation. I know that Claire ran climate workshops for many years on machine learning and climate, and I've attended some of them, and I believe you as well. So there's an AI community that's pretty close to climate researchers, at least on the face of it. And recently, a couple of years ago, there was one of the NSF AI institutes was funded to do research on trustworthy AI, weather, and climate. And, a big component of that is these reproducibility aspects that you were asking about. So I guess I'm curious about what you have seen as the good touching points between the communities, touching points that have not worked, things that you may throw at us as areas that no one has looked at. I'm just really curious about your views on this. And I know we're being recorded. I don't mean to hear anything negative about any of these efforts, but you did say before, if you can, spend 20 graduate students trying to naively apply deep learning methods to these problems that we work on, and it doesn't work. So which of your colleagues are you envious of because they've been able to make great headways using AI? Are your colleagues envious of you because you've been able to make these headways on data curation with us? Just give us a sense for where might be good and not so good touching points between AI and climate.
Yeah, that's such a great and rich question. So let me try to do it justice. As I said, the first thing people try, and it's natural, is just off-the-shelf methods, with like convolutional neural nets or like existing architectures that they just apply naively. And then they found, and actually, so Vipin Kumar had a grad student who worked on that and ended up writing a paper that basically said, we tried the easy things and they didn't work, which is something that I think any climate scientist could have told them ahead of time. But it's good that they were able to find that out for themselves. So actually, Vipin, Deborah, and I collaborated on a proposal last year, which unfortunately was not funded, but the idea would be to do the harder things, tailor the architecture of these neural nets to the actual problems. And Vipin has some experience in this area in hydrology, for instance. So I think that's definitely a promising area. At this point, anybody can use PyTorch or TensorFlow and apply it to basically any data set that they come across. That's not the implementation is not the hard part. It's like, applying the right tools to the right problems. So where I see machine learning doing a lot of service now is in this area of, as I said, sub-grid scale parameterization, of which clouds are one example. So, when you have a grid box that's like this big, but it's so much bigger than the scale of the processes that it's trying to represent, clouds being, perhaps the biggest example of that. the way we've been doing things in the climate community for decades now is using what we call a closure. So basically finding a way to relate the small scale features to the large scale features. And we do this with theory, but there's a lot of fudge factors in there. There's a lot of uncertain parameters basically that are completely unconstrained or very weakly constrained by modern observations. So there are groups, whether it be on land or in the ocean or in the clouds, who are making a lot of headway on that using new data streams, abundant data streams, and basically, I don't exactly know what kind of machine learning methods they use for that. I'm not the person to ask, but I see some interesting work coming into that, where they're basically marrying the physics of the model. So we're still trusting the physics of the models on the scales in which it can represent the processes explicitly, but using machine learning to figure out what's happening within those boxes where the models don't see. So that I see a lot. One issue with this, with scientists in general and AI, is that scientists want explainability. They want traceability. They're not going to be happy with just, well, my AI said this. The next question for a scientist is always, why? How did they arrive at that answer? And I think that's a point of friction a little bit in the communities, where I think, there's a lot of the AI community that's focused more on efficiency and how to get to some kind of optimal answer that, has good generalizability, but not necessarily explainability. So I think that's one area where there can be a lot more crosstalk between the communities.
Thank you.
Hope that helps.
And there is actually an efficiency question in the Q&A. Do you want me to read it?
Oh, sorry. Do you know usual AI DNA training time for this type of prediction or AI training? I think it really depends on what you're trying to do. So for forecasting the weather, or for doing a parameterization of cloud processes within a climate model, so I wouldn't be able to tell you. I know that there's something called DLWP, deep learning weather prediction, where somebody basically people at University of Washington made some kind of neural network emulation of a climate model that they use for prediction. And I think you should be able to find out the information from them about sort of how long it takes to train this model. I know once it's trained, it's basically virtually free to run, but my guess is that all the cost is upfront in terms of how to train it. But I have no idea about the computational complexity. I think it depends a lot on the amount of detail that you want, the spatial resolution, the temporal resolution, and so forth. Any more questions? Yeah, I noticed your internet being a little choppy. Okay, well, it's 12 o'clock, so if there's no more questions, I guess we'll do the one-on-one meetings this afternoon.
Yeah, let's thank Julien for a wonderful talk. And I guess I'll talk to you next week.
Sure. I'll stop the recording.
Yep. Thanks, everyone.